This slideshow will explain how rocks melt by the process of heat transfer melting, which is just another way of saying how rocks melt when we simply heat them up. It's pretty easy to understand what's going on physically with heat transfer melting. The idea is we introduce something into the rocks that heats them up and causes them to melt. Well, what can we introduce into rocks that can carry enough heat to melt them? And it turns out there's really only one thing that is mobile and can carry a large quantity of heat and therefore can rise into rocks and cause them to melt. And that's magma itself. So heat transfer melting always starts with the generation of magma some other way, either by hydration melting or by decompression melting. And then that magma rises due to buoyancy, enters into colder rocks, and eventually heats them to the point where they partially melt. We can see that's going on here on the left. Here we have a magma chamber, and the surrounding rocks here, kind of shown in this orange color, are being heated up, and eventually they'll melt. On a phase diagram, we can show this process pretty simply. We'll start with the rock that's in the surrounding rock, the rock surrounding the magma chamber, and it's sitting here within the field of all solids somewhere along the geotherm. In this particular example, it's at about 850 degrees and about 6 kilobars. And that rock is then invaded with magma. That hot magma then heats up the rock, causing its temperature to increase, but its pressure doesn't change until eventually its temperature exceeds the solidus temperature and the rock partially melts. It generates a small amount of partial melt. That melt gets squeezed out of the rock and then rises due to buoyancy and erupts as a volcano, as shown on the picture on the left. The chemistry of this process is a little bit more involved. Here we have the table summarizing the four basic compositional categories of igneous rocks, ranging from ultramafic on the left to silicic or felsic on the right. And we've talked about how these terms, ultramafic, mafic intermediate, and silicic or felsic, correspond to a composition which can be sort of summarized by the weight percent silica and the amount of iron and magnesium and the amount of the alkali elements sodium and potassium. And we've also noted that the solidus temperature for ultramafic rock is the hottest solidus temperature, the highest solidus temperature, while silicic or felsic rocks have the lowest solidus temperature. Now, if we think about what that means, if the solidus temperature is high, in order to melt that rock, we have to then generate a magma that's even hotter. So we can conclude that the magma temperature of ultramafic compositions must be hottest, and that the composition of silicic or felsic magma must be coolest, and that the temperature of the magma then must change in a way that's similar to the temperature of the solidus of the rock, as shown in the bottom row of this table here. So let's focus then on the the temperatures of as a function of composition of both the rock and the magma. Here I've highlighted those bottom two rows. So the top row here is the solidus temperature of the rock, and the bottom row is the temperature of the magma, of the liquid. And we say that in both cases, ultramafic compositions have the highest solidus temperature and have the highest magmatic temperature, and silicic or felsic compositions have the coolest rock and liquid temperatures. Now, we've already talked about how the process of partial melting results in a liquid that is one step more silicic than the host rock. So in other words, we can show that on this diagram with arrows which connect the temperature, the kind of rock, with the composition of the liquid that's produced by partial melting. So for example, an ultramafic rock here will partially melt to form a mafic liquid, and equivalently or similarly a mafic rock will melt to form an intermediate liquid, etc. Now, it also should make sense now that this liquid now, let's say this mafic liquid, right, can only cause partial melting by the process of heat transfer melting in rocks that have a solidus temperature lower than its temperature. So in other words, we can also on this diagram show the kinds of rocks that can be melted by liquids. And that's what I've shown here with the blue arrows. So the ultramafic magma could potentially melt a mafic rock, because the mafic rock has a solidus temperature that is cooler than the temperature of ultramafic magma. And similarly, a mafic liquid here could presumably melt an intermediate rock, and an intermediate magma could presumably melt a felsic rock. This is simply a function of the fact that the magma, in order to melt the rock, has to be hotter than the solidus temperature of the rock, right? It's got to bring in temperatures and bring in heat such that you can raise the rock above its solidus temperature. So let's think about what happens now at a place like a subduction zone, where we start melting by the process of hydration melting deep inside the mantle. So the mantle rock, remember, consists of ultramafic rock called peridotite. And when that mantle rock undergoes partial melting triggered by the addition of water, it produces a mafic liquid, liquid which, if it's erupted, would turn into, for example, a basalt rock. That liquid, though, rises up from where it was created into the overlying crust. And if that crust, like most continental crust is, consists of largely of intermediate rock, then that mafic magma can potentially melt that intermediate continental crust. When the intermediate continental crust is then melted by the process of heat transfer melting, it in turn produces a liquid that's one step more silicic, or it will produce a silicic or felsic magma. So by this process, we start with an original mafic magma, and as that magma then melts the intermediate continental crust, produces a silicic or felsic magma. And we can imagine then tapping off portions of both of these kinds of magmas, one cooler, the silicic one, and one hotter, the mafic one, and mixing them in various proportions. And if we do that, we can produce magmas that range in composition all the way from mafic to silicic. And indeed, this is one of the primary ways in which we generate the diversity of compositions of magmas that we see in rocks on the crust. So here we can see where those processes occur inside the Earth. We have our subduction zone, which is bringing hydrated minerals, amphibole and serpentine down into the Earth, where they eventually react to release their water, which rises up and triggers melting in the overlying mantle rock by the process of hydration melting. That hydration melting, that partial hydration melting of the ultramafic mantle rock, produces mafic magma. That mafic magma then rises up towards the surface. If, as it rises to the surface, it encounters intermediate rocks such as is characteristic of the continental crust, it can in turn cause heat transfer melting of that continental crust, producing silicic magma. So in these areas shown in yellow here, which represent areas of the intermediate continental crust that are surrounding these hot sources of heat, the mafic magma, we can generate silicic magmas by the process of heat transfer melting. Those silicic magmas can then either erupt directly, or they can mix with the mafic magma to produce any range of different compositions of magmas which are observed to occur within the continental crust.